Hello and welcome everybody. Today we're going to look at Dalton's atomic theory, a very brief video just outlining the precepts of this. This was first published in 1807, more than 200 years ago, and most of it's correct, some little bits are incorrect, and I'll just show in this video what that where those are, okay? So first, atoms are very tiny, right? So, we have this expression, seeing is believing. Well, how do you believe there's an atom if you can't see it? Well, we have techniques nowadays of atomic force microscopy, which can actually image down to individual atoms and molecules. Atoms indeed are extremely small. This scale here shows little features with the red arrows. And there's a scale bar there, 10 angstroms, okay? So that whole molecule in blue, and there's a little AFM image to the left, is 10 angstroms, okay? And an angstrom is 10 to the minus 10th meters, okay? So we've talked about a meter stick. It's this long, guy here. And to imagine that there's 10 to the 10th atoms that you could line up in a line along the length of a meter is just amazing, okay? Now, number two, atoms are identical. Now, I forgot to mention that how small atoms are, okay? So imagine a drop of water. A drop of water contains so many atoms in there, you can't even see them, right? Now, if a drop of water could be divided equally among the 7 billion people on planet Earth, it would provide about 100 billion water molecules to each man, woman, and child on the planet. So they are extremely small, okay? And they are numerous. Now, precept number 2 is atoms are identical. Now, Dalton theorized that all elements are composed of only one type of atom, and that is correct. So if you have a penny, a US penny that is 1982 or before, it's mostly composed of just 100% copper, and those little balls there represent copper atoms. And one copper atom is going to be the same as another copper atom. And now his idea was that all copper atoms are identical to all other copper atoms in a particular mass. Now that's not correct, okay? It turns out that one copper atom could weigh slightly different than another copper atom, and so he was wrong there. He didn't know about isotopes or something called the neutron in the nucleus of an atom. And so we'll look more into this in greater detail in a bit. But that's basically true. All copper atoms are going to be the same as all other copper atoms, and so if copper reacts with nitric acid, we assume that a different penny somewhere else on the planet would also do the same thing. Number 3, atoms are unique, and this is true in all ways, okay? Atoms of one element differ from elements of another element. So on top we have gold, and on the bottom we have copper, okay? So gold atoms and copper atoms will have different properties, okay? Gold is a little bit yellowish, copper is a little bit kind of a reddish bronze type of color, and they're just going to have different properties, okay? If you drop gold into nitric acid, it won't react. If you drop copper in nitric acid, it will react. Gold is unreactive. Copper slowly corrodes depending on the nature of the environment. All right, the next thing is ratios, and this is a little bit harder to understand, but as we get into the chemistry class, this will make much more sense. Now, the idea here, and it's very critical you understand this, is that atoms combine in small whole number ratios. You see, atoms are the smallest component of matter, right? And so if you have the molecule water, it's going to be composed of H2O. We've seen that formula before, probably. And this means that there's 2 hydrogens combining with 1 oxygen. So water has a constant composition of 2 hydrogen and 1 oxygen, okay? And that's just the ratio of elements in the compound. And copper oxide, I'll just call it copper oxide, is composed of 1 copper and 1 oxygen. And here we have a diagram showing some black powder and then a little model of copper 1 oxide and copper 2 oxide, and you can see how there's a constant ratio of copper to oxygen, okay? No matter which part of the sample you analyze and pull out of that powder, it's always going to have a constant small whole number ratio of copper to oxygen. Number 4, atoms are indestructible. So remembered again that this idea that copper reacts with oxygen to form copper oxide. That's the black, kind of a brown or black coating of the on the outside of a very old penny. Okay, and his idea was that atoms are not destroyed. Now, he wasn't thinking about nuclear reactions. Nuclear reactions do indeed destroy atoms and change one element into another element, but that's for a side topic. Most atoms are not destroyed in simple chemical reactions. So here's a chemical reaction. Here on the left, we have oxygen gas in that circle with the red balls there, and then we have on the bottom of this little bottle a chunk of copper. And copper, we've seen the model of that is just a whole bunch of little spheres arranged in a lattice there. And when these two react, they form copper to oxide, this chemical where copper and oxygen are bounded to one another through chemical bonds. And the atoms themselves are not changing or transmuting or magically changing to different elements. They're just rearranging, okay? So the product still has the same number of copper atoms and the same number of oxygen atoms as you had in the starting materials. So that's it about Dalton's law. We use this throughout the course, and it's generally true. Thanks for watching. Please like.